Welcome to The Explainer. So today, we're going to tackle a concept that seems pretty straightforward, but is actually one of the most mind-bending ideas in all of math: infinity. Yeah, it's a word we throw around all the time, but what it really means? Well, it's going to challenge everything you think you know about size itself.
So how do you even measure infinity? Well, maybe the question isn't how big is it, but something a little different. Are some infinities bigger than other infinities? I know, it sounds like a total riddle, but trust me, the answer is going to completely change the way you look at numbers.
All right, let's start with a little thought experiment. On one side, you've got all the counting numbers, 1, 2, 3, 4, and on and on and on forever. And on the other side, we've got a smaller group, just the perfect squares, 1, 4, 9, 16, which also go on forever.
So what does your gut tell you? Which one's bigger? I mean, it seems obvious, right? The counting numbers have to be bigger. The squares are just a part of that set. You've got all those other numbers in between, like 2, 3, 5, 6. So case closed? Well,
To really get to the bottom of this, we've got to look back a bit. Because for centuries, the whole idea of something without an end, something boundless, was frankly kind of terrifying to the greatest thinkers out there.
for a long, long time, people were actually kind of scared of infinity. The ancient Greeks saw it as this chaotic, imperfect mess. You had guys like Zeno coming up with paradoxes that made it seem like you couldn't even walk across a room. So for centuries, thinkers like Aristotle just tried to keep it in a box. They said, okay, infinity is a process, not a thing. But then, calculus came along in the 17th century and basically blew the doors off that box.
So what calculus did was pretty wild. It basically said, hey, let's imagine zooming in on a curve, like way in, until it looks totally straight. It treats every curve as if it's made up of an infinite number of these teeny tiny straight line segments. And these little segments were called infinitesimals. They weren't zero, but they were smaller than any number you could possibly think of.
Yeah, this whole idea was so out there that critics had a field day with it. One famously called them the ghosts of departed quantities. I mean, it's a great line, right? It's because you'd use them for your math and then kind of make them disappear at the end to get the right answer. It worked, but nobody really knew why. Our understanding of infinity was, let's just say, a little shaky. Okay, so this shaky foundation couldn't last forever, right? And it didn't. Enter the hero of our story, a 19th century mathematician named George Cantor. He decided to stop running away from infinity and just, face it head on. So what Cantor figured out was that our brains are basically stuck between two completely different ways of thinking about size. On the one hand, you've got this super old idea that the whole is always bigger than its parts. That's our intuition screaming that the counting numbers are bigger. But then there's this other idea. If you can pair up every single item in two groups perfectly, then the groups have to be the same size.
So he came up with this really simple but totally game-changing idea. He said, look, forget trying to count to infinity. That's impossible. What if we just paired things up? If you can match every item in one set with exactly one item in another set with none left over, then they're the same size. He called this a one-to-one correspondence.
All right, so let's try this with our original puzzle. Can we pair them up? Of course we can. You pair the number 1 with the square one. You pair 2 with 4. 3 gets paired with 9. 4 with 16. You see the pattern, right? For any counting number you can possibly name, there is always one perfect square to match it with, and this goes on forever. And that leads to a conclusion that just completely breaks your brain. The set of all counting numbers and the set of all perfect squares are the exact same size. Our intuition was wrong. When you're dealing with infinity, a part can be the same size as the whole. Mind-blowing, right?
But hold on, because this was just the tip of the iceberg. Cantor's simple little pairing method didn't just solve one paradox, it basically opened up a whole zoo of different infinities. And yes, you heard me right, infinities plural.
He gave this first level of infinity a cool name, Aleph Naught. Aleph is the first letter of the Hebrew alphabet. This is the size of the counting numbers, the even numbers, the odd numbers, the perfect squares. Basically, any set where you could, at least in theory, list out every single member. It's the smallest kind of infinity there is.
So naturally, this leads to a huge question. If Aleph Naught is the smallest infinity, is there a bigger one? I mean, how could there be? If you can list out an infinite set, shouldn't they all be the same size?
This is when Cantor started looking somewhere else. He stopped looking at the nice, neat counting numbers and turned his attention to what we call the continuum, the set of real numbers.
This is everything. All the whole numbers, all the fractions, and all those weird irrational numbers like pi. It's every single possible point on a number line.
And this is where he made his most incredible discovery. He proved, absolutely proved, that it is impossible to pair up the counting numbers with the real numbers. His proof is brilliant. He basically said, okay, pretend you have a list of every single real number. I can show you how to create a new number that I guarantee is not on your list. And his trick always works. It means the real numbers are a completely different kind of infinity, a bigger, denser, uncountable infinity.
And it doesn't stop there. It turns out there isn't just one or two infinities, there's a whole infinite ladder of them. You have Aleph naught, the smallest. The next size up is Aleph 1, then Aleph 2. It's an endless tower of infinities, each one unimaginably bigger than the last.
You know, this discovery was so profound, so completely against everything we feel to be true, that even Cantor himself could barely process it. He wrote a letter to a friend right after he proved it, and he said, "I see it, but I don't believe it." He had created an entirely new branch of math, a world that people now call Cantor's paradise.
So what does all this mean in a more concrete way? What does it feel like to be in a world with a countable infinity? Let's check into a very famous and very strange hotel to find out. Okay, so imagine this hotel. It has an infinite number of rooms, numbered 1, 2, 3, and so on, one for every counting number. It's a hotel the size of Aleph naught, and tonight it is completely booked. Every single room has a guest. The place is full.
The no vacancy sign is lit up bright red. But then, a new traveler walks up to the front desk, asking for a room. The hotel is totally full. Is it possible for the manager to make space for them?
And the answer, amazingly, is yes. The manager just gets on the intercom and asks every guest to please move from their current room, let's call it room N, to the next room over, room N+1. Since there's no last room, everyone just shuffles down one spot. And poof, room 1 is now empty for the new guest. A completely full hotel just made room for one more.
This strange hotel perfectly shows just how weird, but perfectly logical, this idea of a countable infinity really is. The math works, it's consistent, but it leaves us with this huge, lingering question. We can play with these ideas on paper all day long, but could something truly physically infinite actually exist in our universe? And if it did, would it really follow these same bizarre rules? Well, that's a question math alone just can't answer.